Our next set of differentiation rules, or derivative rules, are going to help us work with combinations of functions, in particular products and quotients of functions. Just to give us an idea or an illustration, imagine 4x squared times e to the x is our function. How would we go about differentiating that? I will tell you right now, it is not the naive term by term by term or factor by factor derivative. That is the most common mistake students make. It would be great if it were true. It would make our lives so much simpler, but it simply doesn't work if we go back to the limit definition and try to apply the limit definition to a product of functions. We don't get that simple pattern. Instead, when we have the derivative of a product, there's a simple mnemonic for this. We have the derivative of the first function times the second plus the first function times the derivative of the second. So anytime you see a product of functions, so again, we can ignore scalar constants because those have a simpler rule that we can use instead. But anytime we see a product of functions like x squared times e to the x, each of whose derivative we do know, we can find the derivative of the overall product using this derivative of the first times the second plus first times the derivative of the second. In other words, each function will get differentiated once and then you'll mix and match. Okay, applying that here, the derivative of the first function here would be the derivative of x squared. So that's our derivative of the first. And it's a little ambiguous here. We'll see in more interesting examples later. With e to the x, it's hard to tell if we differentiate it or not. In this case, we're not differentiating. That's just the second function. Plus, you have to be a little bit careful. I'll come back to the brackets in a second. Plus the first function, x squared, times the derivative of the second, or the derivative of e to the x, which is also just e to the x. So how did that work here? We have the first times the derivative of the second. Now we have to be a bit careful. You'll notice that this term doesn't have a 4 in it. There's two different ways we could have handled that. We could have thought of the first term as 4x squared, in which case we get 4 times 2x and 4x squared here. Or we could have simply said that this function is made up of 4 times this entire other thing, and then written it as the derivative inside without the 4's. And again, both of those are perfectly correct interpretations. It's just that one leads to a 4 out front being multiplied through all the terms, and one leads to a 4 already expanded into the individual terms. There's no real difference or preference one way or the other. The key thing for now is to memorize this product rule. A quotient is another possible combination of functions, of course. Like the product rule for multiplication, there's also a rule for dividing or taking quotients. And the rule for here is closely related to the product rule. The one big difference that can sometimes take some memorization is the transition here from a plus to a minus. So what we'll often do is call this function up here the top, and this function down here the bottom. And when we go to take the derivative, what we get is the derivative of the top times the bottom minus, and again think logs. If you think logs, if we have multiplication, when we take a log it turns into addition. Same kind of idea here. When we have a quotient or a dividing by, if we took a log we get a negative sign. So you can think of that as a common relationship. So we have the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. All right, all over the bottom squared. So again, this is a rule that we have to memorize, and it comes from the definition. If you look at the ratio of two functions, or one function divided by another, and do that limit as delta f over delta x goes to 0, then you would get this relationship in every case. All right, let's apply that. Let's jump down to this one here. We'll sneak back up to that original function in a second. just to be able to apply the quotient rule. So here again, I would say this constant is a constant we can put out front of the entire thing. And then our top is our x squared, our bottom is ln of x. Okay. So if we take the derivative of 5 times x squared over ln of x, we take the derivative of the top, which is 2x, times the bottom, which is ln of x, minus the top by itself, the original, times the derivative of the bottom. The derivative of the bottom, the derivative of ln, is 1 over x, all over the bottom squared, the original bottom, all squared. Okay, and that would be our derivative. And once you get to these kinds of scenarios, it's really debatable what advantage there is to doing much simplification. But here we have a nice cancellation. We have 2 x's on the top and an x on the bottom. We might do that. But that's really about all we can do to simplify that particular function. But it's the derivative of what we started with up here. All right, we'll do another quick practice here. Derivative of x times ln of x. This is a product. So we have the derivative of the first, which is 1, times the second, plus, for the product rule, the first times the derivative of the second. And the derivative of ln of x is 1 over x. And we can just tidy that up a little bit. X over x is just 1. So here's a self-checking concept question. Take a look at it, pause the video if you like, and see if you can find the right answer. We'll look at it in a few moments. Okay, so rather than trying to match the derivative here, I think it's most straightforward to actually compute the derivative ourselves and then see which function on the left actually is the correct answer. So we have the derivative of 10 to the x over x cubed. Now that's definitely a quotient rule, so we have to be careful about what we're going to do here. So we're going to use the quotient rule, and we're going to take the derivative of the top, and the derivative of 10 to the x is 10 to the x ln 10. That's from our exponential type rules. And then we multiply that by the bottom, x cubed. Then we're going to subtract off the top itself, divided by, times the derivative of the bottom, which would be 3x squared. So let's add some annotations here. There's our bottom, and then there's our top times the derivative of the bottom. All of that over the original bottom squared. Okay. And actually from that line right there, if we just notice that the denominator can be written as x to the 6th, we can look down and go 10 to the x ln 10, x cubed, minus 10 to the x 3x squared all over x to the 6th. The correct answer is 2 here.